everyone. Thank you so much for being here. Here we're going to talk about static analysis, MLIR, and crucially, automatic differentiation. This work is done in collaboration with William Moses and Oleksandr Zinenko, in addition to my supervisor, Christophe Dubach. Okay, so to motivate this talk and to motivate automatic differentiation more broadly, the computation of gradients is ubiquitous in the fields of machine learning and scientific simulation. It's perhaps, controversially most well-known in the training of deep neural networks, but it's also used in all sorts of like these inverse problems where we have this billiard simulation where you have some initial parameters for your simulation, namely the angle and the amount of force that you apply for your ball. And then you have some target state, which in this case, you want to get the red ball as close as possible to this blue position. And you can backpropagate using derivatives, using automatic differentiation to find these initial parameters that best matches your desired target state. The process of automatic differentiation allows you to automatically generate programs that compute derivatives. And it's very flexible in general, but there are certain limitations with it. Two key limitations are that the generated derivatives tend to be a performance bottleneck. And the second is that there are certain usability challenges that we'll see shortly. Okay, so to talk about these usability challenges, traditionally, the wisdom is that in AD, every part of your program needs to be differentiable. So some pseudocode that kind of describes the physics simulation from before is that you iterate through a bunch of time steps, and then at each point, you advance the simulation forward, and then you also visualize it by rendering it to the screen. However, you might see that an AD system, especially an AD system like Enzyme, might find that you have certain programs that you don't have registered derivatives for, at which point the system will crash because it says, I don't know how to differentiate this. However, you might notice that we're interested in the physics of the problem, but we're not necessarily interested in the obtaining derivatives of all of this rendering OpenGL code, even if it is theoretically possible to obtain these derivatives. So the question is, can we safely ignore parts of our program that are irrelevant? And furthermore, can we ignore these parts of our programs without compromising the correctness of the derivatives that we do care about? The answer to this is this standard technique that's used in autodiff systems called activity analysis, where it improves the usability and the performance of our generated programs through differentiation by ignoring these irrelevant instructions. Prior work in activity analysis has a number of important limitations. The first is that there isn't a correctness guarantee, meaning there isn't like a formal understanding of how to guarantee that our derivative is unaffected by removing these unnecessary instructions if they're truly unnecessary. And the second is that many AD systems have restrictions on the input language that are permitted. For example, if you're using the machine learning library JAX to do your differentiation, you'll need to rewrite your programs if any of them use mutation. There are other systems like Tapenad where you need access to all of the source code being differentiated. And then if you are missing any particular modules, like would be in the case if you're differentiating black box libraries, you'll need to make very conservative guarantees, and the analysis will over-approximate these. So our contribution addresses these limitations by having the following three properties. It is sound, modular, and general. The soundness is done by formalizing our analysis as an abstract interpretation and including a detailed correctness argument. As part of this, we formalize the language we're operating on, MLIR, which we'll talk about in just a second. The second is that it's modular. So it relaxes this restriction of needing a global view of all of the source code that you're differentiating. Instead, it uses function summaries, which is this established approach, and then our contribution is the design of the precise summary such that it can be used in any calling context. Unfortunately, for the sake of time, we probably won't have time to go through the details of this function summary, but those are in the paper. And the third is that it's general. It supports MLIR, which is this compiler infrastructure that is not finite because it's extensible and therefore new operations are always being added to it. Okay, so to talk about how activity analysis can improve the performance of differentiation, assume that we have this function which has two inputs and two outputs. And we are interested in the partial derivative of one of the outputs with respect to one of the inputs. The process of automatic differentiation will yield this generated function, which actually computes a vector Jacobian product. Because our function is two inputs, two outputs, the full derivative, so to speak, is a Jacobian matrix, this 2x2 matrix. And the process of especially reverse mode automatic differentiation will give a general way to extract rows of the Jacobian by changing these additional parameters, the dc and dd. In particular, we're interested in the entry at the left, the top left corner. And to do that, we can set dc to 1 and dd to 0, which hopefully you will see. You perform this vector matrix multiply, and then you get the result that you want. So now we can take a look at an example implementation of what this function might be. And the process of AD, well, for starters, our function has this expensive loop which iterates a bunch of times, does a bunch of work, and it computes the second output, but this loop doesn't matter for the first output. A consequence of this is that when we perform differentiation, the loop results in a loop that iterates in reverse. Effectively, at a very high level, we're kind of iterating through the loop in reverse. And we're doing a bunch of work, but as we saw, because we're only interested in certain partial derivatives, we will call this function setting dc to 1 and dd to 0. And then on lines 13 and 14, we're multiplying dd with another value, which will yield 0. We're adding those. In total, this reverse to loop is adding and multiplying a bunch of zeros and not meaningfully contributing to the partial derivative that we care about. So AD gives us this very general method for computing all of the potential partial derivatives in the Jacobian matrix, but depending on your application, not all of them will be relevant. And activity analysis is a way to communicate this to the system statically at compile time such that these loops won't even be generated in the first place. The sort of high-level intuition for activity analysis is done by reasoning about differential data dependencies as they flow through the various variables and memory allocations in your program. The user will annotate the function being differentiated by saying some of these inputs are active and some of the outputs are active. Then any variable or memory allocation is active if and only if it lies on some path from an active input to an active output. Okay, shifting gears. Why do we target MLIR? And what is MLIR? As I mentioned, it's an extensible compiler infrastructure, which means that it's a language that new operations are continually being added to it. Currently, MLIR is used for a number of things like tensor algebra. It's used a lot in stable HLO, which is used in XLA, which you may know as powering JAX. It's also used in domains such as polyhedral compilation and in quantum computing. This is only like a small sample of the cool things that people do with MLIR. People also use it for like hardware design and other things that are not coming to mind at the moment. And again, like new dialects are being added all the time. And so it's very powerful, there are powerful representations, and we would like to differentiate any MLIR. But then this creates this problem of how do we write an analysis that can grow alongside a growing intermediate representation, a growing language. To do this, we use this concept in MLIR of interfaces. So MLIR includes a number of operations, but we kind of simplify and extract only the necessary pieces of information that we need in each operation. There's a bunch of different ways to have a memory load. And there's a bunch of different ways to allocate memory. There's a bunch of different types of computation that can happen, like a multiplication, but also a convolution or a matrix multiplication. All of these are kind of categorized into these interfaces that extract precisely the information we need to run our static analysis. Okay. Now, we measure the efficacy of our activity analysis by looking at a number of things, including the runtime speedup. So enzyme is the automatic differentiation system that all of this is built into, and it has a prior activity analysis that does not have the same soundness guarantees as this work, which is labeled informal. And then we have two variants of activity analysis done in this work. One which assumes that you have access to all of the source code being differentiated, and another which operates function by function and then only communicates via function summaries operating in this modular fashion. We can see two takeaways. The first is that activity analysis has a non-trivial impact on the performance of the generated derivatives, in some cases up to a 3x speedup, and geomean about a 24% improvement and a 70% improvement, respectively, on the CPU and the GPU for the benchmarks we looked at. The second is that our sound analyses don't lose any of this performance improvement relative to the prior potentially unsound analysis. So formalizing and making our analysis sound did not cost us performance. Another result is that we looked at the various precision of these variants, and although we didn't have time to go into the details of how the modular analysis works, we see that it doesn't lose any precision relative to having access to all of the source code in the program. The third is that we compared the compile time performance of our modular and our whole program analyses. And we see that for smaller benchmarks, the modular analysis has a slightly higher compile time overhead per function, but it does less work as the benchmarks increase in size, which is the case for our GPU benchmarks, which have thousands and thousands of functions in them that are being processed. And we see a significant compile time speed up as a result of our modular analysis relative to the whole program analysis. Okay, so in summary, the computation of gradients is very useful and widespread, but AD can be a performance bottleneck and be difficult to use. So activity analysis enables these faster and more general differentiation procedures by avoiding unnecessary instructions, and this work builds on that by formalizing activity analysis, proving it sound, and generalizing it to work on arbitrary dialects and also mirror the extensibility of MLIR. There's many details that are not included in this talk but can be found in the paper, including detailed operational semantics of the subset of MLIR with which we operate, and full details of how everything is formulated as an abstract interpretation, the function summary design and proofs as to how you can get just as good results with the function summary instead of looking at all the source code. And then there's full correctness proofs for everything mentioned. All right, thank you so much.
Any questions? Okay, while the audience warming up, may I request the next speaker to be ready? Yeah, I have one question for you.
Yes.
So if I have a function which has, where you're creating the summaries for functions, right?
Yes.
If that function has other function calls which are not easily resolvable, say function pointers or virtual calls, how do you deal with them?
Great question. Regarding indirect function calls, we currently do not. Yes, because it creates a compound problem of trying to resolve like which of the possible call sites are being called. One potential approach is to try to do like a union of the different potential points to candidates of which functions could be pointed to. But yeah, it is challenging.